Welcome back, guys. We're going to try to consolidate today the knowledge you already have about the 16 segment displays. So here is a common anode display connected right here. And we're going to focus now on the diagram making the checking. So basically, we're going to have to build a counter. The thing about the counters is you can work in different ways building them, like having a binary counter. So depending on the number of stages built inside from flip-flops, you can calculate what's going to be the maximum number of combinations you are going to get. So in other words, what's going to be the maximum number I can get. So for the binary counters, the total number of combinations is going to be something like the binary raised to the power n, where n is the number of stages. Example, if I have 4 stages, I can count 2 to the 4th power, which is 16 combinations, okay? So if I count to start from 0, I'm going to count up to 15, 0, 1, 2, 3, up to 15. If I'm building a counter based on the Johnson's counting, then it's going to be with the same number of stages 2 times the number of stages. Like if you have 5 stages, it's going to be, example, instead of being 2 to the 5th, it's going to be 2 times 5 is going to be 10 combinations. Why am I telling you that? Because we try to make the simplest possible diagram for checking. So the simplest one I found is based on the Johnson's counting. And I've just made a copy of one of an old manual of Ray Marston. Okay, here is the page number. It's called CMOS IC's manual, something like that. It's an old manual. I put even here the page number, but the thing of the diagram is, even if I found it fully functional, actually, there are missing information here, like even if this package looks like exactly that one here, it's forgotten the notation of it. There are no pin numbers for the outputs here. So forget about this one. And I'm going to pick up here a magnified diagram. I simplified. And whatever is in red are the pin numbers of the package. The package number is 4017. So if I'm coming back here, we can build a binary counter easily. We have good packages like 7493 for binary. If we only want to limit it to decimal counting, we can take its counterpart 74192. And if we want to get the CMOS, because we're going to energize everything from 12 volts today, we're going to make the counterpart 4192. Okay, so we can build binary counters. But for the Johnson's counter, one of the most commonly used circuits for counting, it's a package called 4017. Okay, so that's what I found. Using that package, you can get the simplest possible diagram. Okay, and here it is. So from the manual of Ray Marston, I picked the diagram. I checked it, everything is just fine, but there were missing numbers here. So whatever is in red, there are pin numbers. And let me explain very quickly what does it do. In the moment you use a diagram, you have to keep in mind what is the goal for it. So our goal is what? Is to check our 16 segments of the display, but the display does not only contain 16 things to check. It's the 17th one, which is the decimal point. So you have to build a counter counting something like 17 positions. And that's exactly what's here. This kind of 4017, it's made theoretically to count 10 things because it has 5 stages, and again, in the Johnson's counting, 2 times 5 is 10. However, when you combine these two counters together, there are a couple of pins you are going to lose when combining them. You're going to lose, for instance, from the first package, the last output here. The last output because it's going to be used to trigger the next circuit. And from the second package, you're going to lose the first output and the last one. Maybe it's not a moment to discuss in detail about the package 4017. However, in the moment you put the power on and you energize it, the output 0 goes by default on. So this is why for the first package it's okay to see the 0, the first output, but not for the second package because you don't want to see that one here, okay? So you're going to lose this one, and you're going to lose also the last one because it's involved in re-triggering the whole thing again. So what happens is you have available right now the outputs we call, let's say the output 1, 2, 3, 4, 5, and so on up to 9. And then you continue with the outputs 10, 11, 12, up to 17. So you're going to have 17 outputs for these two counters because you want to control 17 things. I call them things because they are not 17 LEDs. Remember, there is only one LED here for the decimal point, but each half segment contains 2 LEDs in series, and each full segment, it contains 2 groups of 2 LEDs in parallel. So there are 2 diodes in series, there are 2 others in series, and these 2 groups are connected in parallel. And for that reason, I call them things and not LEDs because we talk about segments, okay? Some segments, they contain 1 LED, some others, they contain 2 LEDs, and some others, they contain 2 groups of 2 LEDs. However, there are 17 things, okay? And when counting 1, 2, 3, and so on up to 17, then we want what? We want to reset the whole thing and to restart to count again. Like here, if I'm putting it on the automatic work, we can even modify the speed, of course, as you've seen it already. So then what happens, I want to reset the whole thing. And because of this, I want to send a pulse to reset the whole stuff and to restart again. And this here, that little circuit, it sends the pulse to reset. Now, let me take some note on my little notebook here, because then I have to clarify next time some other things like what is a pulse, and then what is a monostable circuit. Why? Because that circuit here, made of 2 NOR gates, a capacitor and a resistor, is a very, very simple monostable circuit. What does it mean? It sends just 1 pulse when it receives an input here from the last output, the pin 11. It creates just 1 pulse, a short one. It's something about 15 microseconds, a very short one to reset both packages. As you can see, from here, the signal goes on the pin 15, which is the reset, and to the other package, the pin 15, which is the reset. So basically that's it. As soon as you give input clock pulses, the clock advances from the position, from the initial position, the logic output 0, because remember you want to figure numbers 0, 1, 2, 3, up to 9. So we call this the first output, the second, the third, the fourth, and so on. And then after the 17th output, everything goes back again. As you can see, it doesn't stop, okay? And forget for a moment about our 16-segment display. I'm going to disconnect it to not bother anymore. What's here, though, is you can see the counter advancing. Okay, power off, power on. So it starts from the first output, and it advances 1 position at a time. So all the outputs are on, excepting for the one advancing, okay? And if we want to be slower and to have a control, and this is what I recommend to everybody when doing such a circuit, is to have a manual control over it, so you control and to stop anytime you need to take a breath. Okay, example, the first output now is different from the others. Now I advance to the next, I can stop anytime, to the next, to the next, to the next, and so on. So I can exercise a full control over the diagram, you see, a full control over the diagram, and I can stop it anytime. Okay. Surely the easiest way is to have an automatic advancement, because you don't do big deal, you just watch the diagram working, and the only thing you may possibly adjust is the speed. Okay, so if you wanted to adjust the speed, is okay, you can make it much lower, but this is the automatic work. We focus today on the manual. Okay, and here these are actually the bar graphs. I was actually showing them before, exactly the bar graphs, and the similar counter to this, but made with the TTL circuits and not with the CMOS, is in a sequence of 2 videos, decoder ICs in shallow water. Okay, so if you go back and you watch the first video in the sequence of 2, you are going to find a similar circuit by made with TTL integrated circuits. The problem is, this is the simplest diagram we can make to only count 17 positions. Okay, exactly 17, not 16, not 15, and so on. However, of course, you can modify the diagram to count, because for these 2 packages they can count to maximum 17. But if you move this pin to trigger the reset from here, from the last output to one of the previous outputs of the second package, you can modify this counter to count, let's say, if you want to count to 11, to 12, to 13, to 15, to 16, not necessarily to 17. You just move this wire from here to one of the previous outputs. But I took advantage of the fact that the maximum capability of these 2 packages is going to 17, because that's exactly what we need. So in total we have 2 packages here, plus 1/3 package containing the 3 gates. The package 4001 actually contains 4, but we don't need the 4th one. So we use the 3rd package to create the monostable circuit, and here we just need an inverter. Okay, so is the minimum you can get for such a diagram counting to 17, 3 packages. So now, how do we connect all this to make it working for us? Okay, right now what I have here again is a Common Anode package, and the way the bar graphs are connected in a Common Anode. Exactly as I was telling you in a previous video, the decoder ICs in shallow water, when we take a look at this bar graph, if you count, this one has exactly 10 positions, and what's inside? There are pins on both sides, so each pair of pins, top and bottom, they represent 1 diode. Okay, so let's say we want to have them connected in a configuration with a Common Anode. So guess what? From each output you are going to have something like this. So you're going to have a resistor here. Let's say you can put any resistor you want, around 500 ohms. Okay. And the second one is going to be the same, and the third one is going to be the same. And so on. And the next one is going to be the same. Okay, let me see. It's a yes, Common Anode. So all the anodes are together here through these resistors. And of course I used for that the ones you already know, the network resistors. So all the resistors there, they go to the ground, okay? They go to the ground right here, okay? Oh. It's a common anode, so they go to the positive voltage. All of them, they go to the positive voltage. They are simply protected by the limiting resistors, okay? So everything is like that, okay? Now, because of this, anytime a pulse is coming, the counter is advancing, okay? And it re-triggers everything from scratch when you reach the last output, okay? So this is because we have, for the common anode configuration. This is why when I want to connect my digit, this is the common of the digit, I'm going to connect it to the positive, okay? Because the digit is a common anode, okay? Let's modify it now. And I want to connect a common cathode. So I'm going to remove my digit from here. You can see now it was a common anode. And I'm going to connect now a common cathode one, okay? For a common cathode, okay, we plug it here. But now, because it's a common cathode, we're going to move the common to the negative of the supply. And we're going to move the common of the network resistors to the negative of the supply also, okay? And I'm going to take another diagram. It's absolutely similar to the previous one, okay? And now, when I put the power on, what happens now, because that's a common cathode, instead of having all the LEDs on, all the lights on the segment, before the decimal point was off, now it is on. And anytime you want to press, it's going to be one LED at a time. And anytime it's reaching 17, it's restarting from 0. Okay, that's because you connected now the common anode, the common cathode, sorry. And then, of course, you can modify the speed exactly like for the other one. But the way it's working is a bit different because it's a common cathode display, okay? So now, how do we connect for the common cathode? How do we connect? Because we only disconnected 3 wires. The 2 commons here for the 2 network resistors, because it's 1 per package, and the common for the whole digit. So from this one, let's say, from the number 1, you're going to have this kind of arrangement. This time, the common is the ground. So this is why the cathode of the diode is here and the anode is here, okay? And all of them are going to have, let's say this one, they are going to be oriented like this, okay? I didn't need to change my the position of my bar graphs, simply because it's a kind of bicolor bar graph. So I could leave them in place. This is why the color changed. It was a red before, now it's a green, okay? Cathode, anode, and so on. And if I pick up another one from here, it's going to be a similar arrangement, like that. Okay? So now, how can we make this counter to advance? I said you can make it automatic. Now it's on automatic, but you can make it manual, okay? Manual meaning only when you apply a pulse, one at a time, okay? So I'm going to draw here a circuit which is determining the manual advancement. And for this, what I'm going to use? I'm going to use a micro switch. Not this one. This is exactly the one like you have in your microwave oven when you open the door or you close it. It's too big, but it's still a micro switch. I'm going to pick up a miniature one, okay? And like any micro switch, it has three contacts, a common, normally open, and normally closed. And I'm going to use a simple flip-flop to connect it to our circuit. So let's put it right here. If I'm quickly making it now. Okay, let's say 10 kilo ohm resistors. The package is going to be 4011 to keep working with the CMOS circuits, NAND gates. So this guy here is the micro switch. There's the common contact, common, because it's common to the other two. This is the normally closed, there's the normally open, okay? And talking about pulses, here what you're going to get. This here, because it's an open circuit, you're gonna have the full voltage coming through that resistor to one of the inputs. And here, that contact normally closed, it collects the 0 from the ground, and 0, it doesn't matter what the other input is, 0 times anything else is a 0, so you're gonna get a 1 here. 1 coming from here on the line as the second input of this one, where the other input was already a 1, so 1 times 1 was a 1, so here you have a 0. So initially, this one is a flat line on the 0 logic, and as soon as you press that micro switch, the arrow from here, it moves over here. So because it moves over here, it collects the ground and it brings it over here. So 0 times the other input is going to be a 0, and you get a 1. So that's how you get your pulse. Okay. So here, that level here is for the 1 logic. Okay. That's a 0 logic, and that's a 1 logic. So that's the pulse I put on my notebook to clarify next time. Okay. So this is going to go where? This, let's say, if I want to just monitor it, I can simply connect an LED like this. Put a 1 kilo ohm resistor, one LED here. And if you take a look at this tiny LED over here, which is now off, as soon as I press the button, it goes on, you see? So it's 0, it goes on. 0 or off, it goes on, off, on, off. So anytime I press it, just to monitor that the circuit is working fine, it's gonna be on. Surely we can put here some pin numbers. This is number 1, this is 2, this is 3, this is 4, 5, and 6. I only need 2 gates of the package. So as all the simple 14-pin packages is going to have the ground on the pin 7, is going to have the positive voltage on the pin 14, okay? So that's how you do the connections right here. Now what do? I'm gonna put this in red because it's more visible. Right now I'm gonna pick it up from here. So from the pin number 3 is going over here and connect it right to the input. And that's how, by pressing the micro switch, I'm gonna be able to bring the signal over here to make my counter operating, okay? And remember, this time is in a common cathode configuration because all these cathodes, they are together to the ground, okay? So you could put the diodes right here and the resistor up and so on, but for me it was easier because the resistors being network resistors, they had a common already, I could connect to the ground, okay? So that's the difference between the two diagrams. In the other diagram with the common anode, you had the cathodes of the diodes in the top. Now you have the cathodes in the bottom and the anodes in the top, okay? So that's the circuit controlling the 16 segment display plus the decimal point, okay? So focusing again on the manual control and not on the automatic, because the automatic, it involves another kind of circuit I have to clarify. The A-stable circuit. It's called A-stable because it's not stable. What does it mean it's not stable? It means that it does not remain in a stable state, it moves all the time, okay? So this is the A-stable circuit. So again, pulse, monostable. Again, monostable is this guy here used for the reset. And the A-stable circuit, the one we didn't discuss today because it requires a very special attention, even if it is made using a very classical 555 integrated circuit that everybody seems to know. However, there are some little problems when using it, okay? So today we only focused on what? We focused on this diagram over here where we connect a simple flip-flop with a micro switch to give manual pulses to the counter and to the counter itself. And again, it's practically impossible to find a simpler diagram doing this thing, to count 17 positions, exactly the ones we need, okay? A diagram only containing 3 integrated circuits, okay? So, thank you very much for today. See you next time. Bye-bye.